Yeah, so hi everyone, I'm Remco and I'm working on the ComPWA project, which, as Eduardo already mentioned, is a project for amplitude analysis. So we offer several Python libraries and websites that facilitate amplitude analysis. But I'm actually want to focus on a technique that we use that could be useful for more general audience that has an interest in differentiable programming. But before I go into the notebook itself, and before we look at the code, a bit of background. So as I said, I come from the world of amplitude analysis, and generally the problem that we try to tackle is that we want to know what happens in between some initial and the final state. We're interested in what kind of intermediate hadronic states could be there. So if we have this J psi decay into sigma k p bar, we hypothesize that there could be 3 different kinds of subchannels. And each of these subchannels can then have several resonances of different spin and angular momenta and energies. And the challenge now is to find models that most accurately describe the distributions as we see them. Now, what's difficult in amplitude analysis is that these models are very complicated. You have several interference effects that you need to take into account. And well, on the top level, the full expression is still kind of recognizable. We have the 3 terms for the 3 subsystems here. But each of these amplitudes here, they have to be aligned to take certain spin effects into account. And you have to compute helicity angles there from the form momenta that you measure. And then each of these sub amplitudes, they are also again a large sum of spin projection terms. And in turn, these ones also have certain parameterizations for the dynamics for dynamical effects. Now, as you can imagine, these kind of models, they are very sensitive to fluctuations. So you actually do not want to bin your data. You work with unbinned fits, and therefore you want to have very high performance computing so that you can quickly try out a new model and then run a new fit. So that's one side of the story. You need performance, but I want to emphasize this flexibility that you do. If you have some theoretician who says like, "Okay, could you please try out this different dynamics line shift?" You don't want to have to re-implement everything. You need this flexibility to quickly try out new things as well. So we have been thinking, how can we make this easier to do, so that you bring the implemented code a bit closer to the theory that you are trying to implement. And 2 main ingredients that we use are these computational backends that have become available for machine learning and data science. I bundle them under the term differentiable programming. And the other is the introduction of a computer algebra system. And that gives you, well, the 2 main ingredients that I just saw. The small that I just mentioned. The small consequence is that you also kind of automatically document what you're doing. So that's well, we'll see that that's a quite nice side effect. So I guess that I've well that you've seen all these frameworks for machine learning before. I mean, Nathan was also just mentioning them in the talk. They've become available since the past few years, and what we use in amplitude analysis, what we want to use of these frameworks is not really the machine learning part, but just the fact that they can very efficiently compute very large expression trees, so that you can, for instance, quickly evaluate some gradient descent algorithm. A few techniques that we use there are factorization. So that you, as a Python coder, you just write some simple function, and then the framework itself does the heavy lifting of multiplying, of doing the matrix multiplications. They also come with different techniques like XLA that kind of convert your code into device agnostic code, so that you can easily distribute your processes to CPU or to GPU. And a very exciting thing, and that's what we have already seen being used in Nathan's talk, is this automatic differentiation. So if you have a certain function, most of these frameworks, they can automatically create a new function that can give you the gradient of this function with respect to certain arguments. But anyway, as a Python user, you usually only have to worry about writing a function like this. And we use this effect to insert a computer algebra system. So first of all, what is a computer algebra system? In Python, the natural choice is to use SymPy. And well, we have a small example here where we write a full small expression built up of symbols. But we should realize that what we see here, this is just some output from a Jupyter notebook, is just a rendering of what SymPy is doing in the back. SymPy represents this expression here as a tree of fundamental mathematical operations. And well, we recognize this graph already from the previous slide. And as you can imagine, this can serve now as a template to those computational backends. And in SymPy, this is called code generation or lengthification. So here we have a slightly more complicated expression tree. And then we use SymPy to, for instance, generate Fortran code. This is just a different representation of the tree you see here, or C++ code, or what we are interested in, some JAX code here. Now, a very cool thing to realize now is that a computer algebra system can do analytic simplifications of these expression trees. I'll show you a few examples in the notebook. But if you have this easy conversion of the expression tree to this code, that also means that these analytic simplifications result in numerical optimizations in the numerical computations, right? So I mentioned ComPWA. This is a set of libraries that we offer. The first two packages here, QRules and mform, are encode just the kind of automated process of finding the resonances that you're looking for, as well as formulating the expression, the amplitude model as a symbolic expression. But for our purposes, the latter library, TensorWaves, is more interesting because that kind of streamlines the process of converting the symbolic expressions to those backends. It kind of wraps around SymPy. So as I said, the first two packages, they kind of standardize amplitude analysis. That you have a single source of truth without having to worry about the computations. And then TensorWave does the conversion, and it also comes with some functionality to generate hit and miss Monte Carlo samples, and it interfaces to filters like iMinuit. Right, as I mentioned, another consequence of working with a computer algebra system is that you immediately see the expressions that you're implementing. So that's obviously quite a nice thing if you're doing some analysis. Right. I won't in this talk show you a full amplitude analysis. So here's a very short example of a very large expression. I mean, it will take a bit too much time to render that in a notebook. And what we see here is we have converted this large expression of more than 40,000 mathematical operations into a JAX function, and then we evaluate it over a number of data samples. So the largest one here is 30 million, and you see that it still takes less than a minute on a single CPU to evaluate it. So that's already a nice sign that things work. What we do in the second case, we substitute analytically the certain parameters with expected values, and we do that with SymPy. We just analytically substitute them, and that has a nice effect on the performance as well. So let's now have a look at the notebook itself. Oh, just a small thing. I don't have the luxury of having two screens here, so let me quickly have a look at the questions here. I wonder this as well. So this is like, I wonder if there are other projects that have used this idea. I'm not aware of any, and this is actually one of the reasons why I show it. It's just to show the idea, and maybe others are also interested in trying it out. So it's not as much as presenting this ComPWA library, it's more about presenting the idea. In fact, it would even be interesting to have a kind of a dedicated talk next year on computer algebra systems or SymPy, but okay. Let's have a look at the notebook now. I have a small cell that just hides all of the matplotlib stuff because we're not too interested in that. So first of all, in SymPy, if you formulate an expression, you have to define certain symbols. and then you apply some mathematical operations on them so that you form your expression. So we have here formulated a small Gaussian, and the nice thing in SymPy is that you can then analytically simplify, substitute things. We do some substitution here, and of course, things are done in SymPy are done very exactly. So if you would substitute this sigma with a square root, it also exactly replaces that square root with a 4 in this case. But the problem is it's not suitable for fast computations. So SymPy comes with this leptification. We have here the SymPy leptify function that takes an expression, and then you have to give it an order for the function argument. So if we have a look at what this resulting function looks like, we see the arguments here, and we have a certain NumPy function here. So the import for the NumPy exponential function is also handled automatically here. And yeah, as I said, this is actually suitable for vectorized computation, so we can do stuff like plotting things. Right. Oh wait, let's go the other direction. Yeah. Now, TensorWaves is wrapping around this system of leptification. It does some additional. It has some additional functions like making the JIT compilation work better, and it also kind of takes care of the argument handling. So you saw just now that you have to think about where you want to place your arguments, but this is handled automatically in TensorWaves. So let's just have a look at an example here. Look at me while there's no questions. We have here, in this case, a two-dimensional expression. So we have x and y as input, and we have here the equivalent of the SymPy leptify function, but then for TensorWaves, and we create 3 different types of functions for the three backends: NumPy, TensorFlow, and JAX. And what's important to note here is that you don't have to worry about the argument order. So this is handled by TensorWaves. It just extracts like, hey, there are 3 symbols here, or 2 symbols. So that's what we need as input. This also means that I want to go to the next slide, but yeah, there we go. This also means that the input for the function somehow needs to account for the fact that we have two-dimensional data. So we work with dictionaries where we just use the name of the symbol. Another reason to work with these strings is that in SymPy, if you convert a symbol that has backslashes and stuff, this results in problems with the function arguments. And well, in a string you don't have this problem. So indeed, if we feed this data sample to the NumPy function, you have a NumPy array as a result, and for the TF function, you have a TensorFlow tensor, and for JAX, you get this JAX device array. Right. So that's one of the tricks. Now, TensorWaves is intended for doing fitting, right? So we also have to have a way of taking care of symbols that are intended as parameters. So here we have again an expression that we want to be two-dimensional, taking the r and phi for like polar coordinates as arguments, and the rest of the symbols should be considered parameters that are to be optimized. So there's again like the equivalent of SymPy leptify, but in this case we tell the function that these symbols here, the d phi, the kr, and so they are to be considered as parameters. They are carried around by that function, and they are given a certain initial value so that you can later on tweak them or optimize them. Now, imagine that you want to work with that you measure your data in Cartesian coordinates. You want to convert those Cartesian coordinates to polar coordinates. This can also be done symbolically. So here you have symbolic expressions for the conversion to from Cartesian to polar. And TensorWaves has, again, a kind of SymPy elliptification equivalent where we can work with these kind of multi-dimensional expressions. So in this case, you see that we have indeed some JAX functions that take as argument x and y and that return r and phi. Right. So this is a bit of more complicated block of code. What we see here is some wrapper classes from TensorWaves that allow you to generate a block domain. In this case, with for the Cartesian coordinates. So this is just going to be a block of data. Then you want to use a hit and miss strategy or acceptance and rejection strategy to generate data sample based on those on that function that we just saw, that polar function. But the problem is, of course, that you need to convert the input data that is generated by the domain generator to the to polar coordinates. So that's why you have to give this converter here as well. And indeed, the result is again the array a data array in terms of r and phi. So let's have a quick look at what this looks like. Apologies, I have to move back. There's just a problem in this rise thing. But yeah, indeed, the distributions look nice as we expected. And yeah, as I mentioned, the function that we created is a parameterized function, so you can also play around with the arguments here. Now this is just done to create some fancy widget, but of course you want to use this to optimize your function. I'm thinking now if I could continue with a smaller example where we do a fit, or I could continue with an example where we do a fit for an amplitude analysis. Let me first have a quick look if there are any questions. From Jim, I've heard that cluster organizations suffer from expressions well. I'm not sure. We could also, if Jim wants to elaborate on this question, we could do it later on as well.
Sure thing.
But, yeah. You want to tackle this question now or continue with the
later? It's a general question.
Okay, right. So yeah, let's just I'm thinking like actually let's continue with the amplitude analysis and not so much a smaller fit example. So for this we need the two packages that are used to formulate these larger symbolic expressions. First of all, there's QRules, which, as I said, can automatically generate certain resonances that you would expect to appear between initial and final state. So in this case, we have a J psi decaying to gamma pi pi, and then we use the very nice scikit-HEP particle package to fetch like quantum numbers. QRules then comes also with several conservation rules that then check which particles will be allowed in between. So in this case, we have just limited our allowed intermediate particles to these F0 resonances. And then you see the system finds 5 resonances here. This is an extremely simple example, but it's nice to illustrate to illustrate a slightly larger expression. So then we use the second library, mform, to build up an amplitude expression. As I said, it's a simpler one in this case, where we don't have these kind of interference effects from different subsystems, but still the expressions for these sub-amplitudes are still relatively complicated. You have these kind of form factors, you have a whole bright Wigner, and then you have again these isospin Wigner D functions. So if you plug all of those expressions together, you have a larger expression of, in this case, about almost 1700 mathematical operations. And we can ask ourselves the question now, can we simplify a subcomponent of those expressions? We have a look at one of the nodes here. So as you can imagine, you have an expression tree where you just, in each node, you have a look at the first argument and the first one and the first one. and then we end up at this this particular function here. Now you can imagine, for instance, that you want to substitute these masses of the decay products M1 and 2, or in case you you want to keep certain parameters fixed, you want to substitute them analytically beforehand. And that's what we're going to do here. So we have a certain set of parameters that, of which we guess the value. So there's a coefficient that we tweak. We have certain masses that we want to be able to tweak, and certain widths of those resonances. We can then make a distinction between the parameters that are still remaining, or the symbols that are still remaining. Those are given by the model itself. The values are also inserted from the particle package. So the particle package, of course, comes with mass values, and they come with an initial guess. So that's what we do here. We substitute the fixed parameters, and then we have a simplified expression here. So let's have a look at the effect. It's let's go back. We have here the original expression, and then the second one. It's slightly less complicated, but still, it's just to show you the idea. You can, as you can imagine, you can make further simplifications, like you can kick out this square root, and as I mentioned, also you can make these decay product masses scalar as well. So it's just an example. Right. So again, we use this create parameterized function to make a parameterized intensity function. I'm just going a bit fast now because then we have some time to discuss things. Oh, it is again getting stuck here for a second. We also need to generate data, and here this conversion from the different data samples, or in this case, 4 momenta comes in handy. So we have as input, we have 4 momenta, but we want to work with those helicity angles. So this is almost like this conversion from Cartesian to polar coordinates, but then from 4 momenta to helicity angles. It's quite a larger type of expression. So it's a bit slower than I had hoped. I remember that Jim gave a talk on this rise thing and mentioned there are several disadvantages which I experience now, which is, there we go. We need to generate a data sample as well. So the previous one was just a phase-based sample so that we can do an unbinned fit. And there we go. So we have generated the data sample for this function with hit and miss strategy. That will be our test sample. Normally you would take data from an experiment. Then we have given a certain parameter guess, updated that, and we see that it looks like a bit nonsensical. So what we're going to do is we use the unbinned negative log likelihood method to optimize our function with regard to a data sample. And there we go. And the nice thing in TensorWave is that you can insert callbacks, with which you can insert custom behavior into your fit process. In this case, we want to register how the parameters develop over time. So the fit result has some kind of the most useful, like the most common results that you want to have. It also passes on information from iMinuit so that you can get like the covariance matrix. And the fit indeed worked out nicely. We have the same result. And this is the result from, let me go back again. This is the result from the callback where you register the values of the parameters over time as well as the estimator. Right. So I guess that leaves 4 minutes for some discussion. I've heard how much overlap is there between JIT compilation. And could you do this? could you do this by itself or in the CAS? So I'm not sure if, okay, so JIT compilation is just performed over the generated code. So you have SymPy lamplification where you generate code. And in this, I showed it in the slides, right? Let me just go back to the slides here. I have been slightly dishonest here. So what SymPy actually generates is this part of the code. And what TensorWaves then does is give this additional decorator so that the code is JIT compiled. But in principle, it's just separate from SymPy or from the Computer Algebra System. Not sure if that answers the question though.
Right, I was asking the question, maybe a brief follow-up. So what I'm wondering is essentially if you skip the first simplification round, how much can the compilation do of the simplification that the Computer Algebra System would have done otherwise?
Yeah, I actually have the impression that SymPy already does a lot of simplifications. Sorry, JAX does a lot of simplifications there. One thing that I'm sure about though is things like trigonometric functions. So this is especially important in amplitude analysis, where you compute these angles and you plug them into Wigner-D functions. So like you have to do some additional tricks here, but SymPy could simplify that. So you have like a sine of a cosine, and JAX would, as far as I know, not be able to make that easier. This is something that we have to investigate if we can make this easier to do. But more linear simplifications, I have the impression that JAX does do that.
Okay, thank you very much.
Yeah. Now, Jim, you had a question as well, right?
Yeah, so my question was kind of general, and I think also similar to the last one, at the base motivations of this. So I've often heard in introductions first introducing AutoDiff, they start by saying, well, you could symbolically compute derivatives, but then the size of the expressions swell, they just get bigger and bigger. But you're not finding that to be the case? Is that because of something special about partial wave analysis, or?
No, okay, now I see what you mean. So you mean because of like a product rule that you have like you already have a large expression. If you then take the derivative, it becomes even larger, right?
Right.
So this is, yeah, and this is indeed an effect that we see. So in the example that I just showed you, we do not use an analytic gradient, but I have talked with Lucas Heinrich of PyHEP, and he was like, well, this should actually not be a problem. So at the moment, there are, of course, these wrappers around the functions, and I have the impression that it has something to do with that, actually. But I mean, so to answer your question, I hear different stories. Yeah. All right. So I see no other questions, and it is past.
Yeah, I think we normally perfectly time.